All right, let's get started. So pick up where we left off last time and redo the last proofs that we did last time. Talking about subtraction. So with modular arithmetic, addition and multiplication were pretty straightforward, right? So now we're going to do subtraction. Rather than the way the author does it, where he tries to uniquely define, try to show that there is a unique number that satisfies this equation, and then show that that number is this number, I'm going to do it all in one proof to save the headache of doing the exact same thing twice and trying to figure out why on earth the author is doing the same thing twice. So this is combining two things in the book into one. So let n be a positive integer and let a and b be in Zn. You with me so far? You remember what Zn is?
Always. Like
Where's Rhoda?
She went to lunch with someone.
Alright. So Zn, this is all the integers from 0 all the way up to n minus 1. So first n natural numbers. There's the right way to say it. The first n natural numbers. Okay. So let n be some positive integer and let a be in Zn. Then there's just one and only one, x in Zn, such that a plus x is equal to b, namely x equal to b minus a mod n. We will later define this one and only x to be what we mean by b minus a. With me? Okay. So we're going to prove that this thing right here is in Zn, that this thing right here is a solution to this, and then that this thing right here is the only solution to this. With me? Okay, so let's prove. So let x equal b minus a mod n. Now, notice, this is something that we're going to be using later, so this is just something to notice right out the door. Notice that this says the exact same thing as there exists some integer q such that b minus a is equal to q times n plus x. If x is equal to the mod of those two, the remainder, when you divide this by this, that says the exact same thing as that. We're in the same equation two ways. With me so far? Okay. So, observe that x is in Zn. How do we know x is in Zn?
So it has to be between 0 and...
Yeah, it's the remainder. It has to be between 0 and n. That's exactly what z sub n is. All the integers, all the natural numbers from 0 to n, not including n. So x is in there. Good so far? Okay. So observe that x is in Zn, and that we can rewrite x this way. Now this is the only time I'm going to baby walk you through doing this. From here on out, when I have something like this, I'm going to go straight to an equation like this. If I say x is equal to b minus a mod n, that is identical to saying x is equal to b minus a plus some integer times n. From here on out, when we have this, I'm going to go straight to this, and we're not going to walk you through this middle step. You good? Okay. And it makes intuitive sense, hopefully. If x is equal to b minus a mod n, then x is going to be b minus a plus some integer multiple of n. It could have only been adjusted by some integer multiple of n. Anyways, but here's the baby step way. That to that to that. If you ever get confused, you can always do it that way. I'm just not going to do it again, and we're going to reference this a lot going forward, so be comfortable with that. Okay, so then remember what we're trying to show. So first thing we showed is that x is in Zn. Now we need to show it's a solution to this thing. And then we'll show it's a unique solution. So now let's show that x is a solution to this thing. So then let's look at a plus x. That's the same thing as a plus x mod n. That was the definition of this addition, right? Remember that? So here to here, just using the definition. Now, a minus a goes out, and we're left with b plus some integer times n mod n. That's the same thing as just b. You with me on that? If we take this thing and we divide it by n, our remainder is going to be b. Good? All right. So we just barely showed that x is a solution to this thing. Now we need to show it's a unique solution. In case you last check what we did, we showed a plus x is equal to b. We showed a plus x is equal to b. That's what we did here. Okay. Okay. So we showed x is a solution. Now we need to show it's the only solution. So assume by way of contradiction that there are two things in Zn that aren't the same things and are both solutions to that equation. Good? We're going to show that they're actually equal to each other, contradicting the fact that we said let them not be equal to each other. So then x plus a is the same thing as x plus a mod n is the same thing as x plus a plus some integer times n. Similarly, y plus a is y plus a mod n is the same thing as y plus a plus some integer times n, called k and k prime. Could be the same, might be different, but for sure we can express them both that way, right?
Yeah.
Now, since x plus a is equal to b and y plus a is equal to b, then x plus a is equal to y plus a. So x plus a is equal to y plus a. So x plus a is equal to y plus a. With me on where we are right here? Okay? Subtract the a's from both sides, and now I'm going to put my x and my y on this side, and my n's on that side. So my a's cancel out, so you can ignore the a's now. I'm going to get x minus y when I move the y over here, and I'm going to get k prime times n minus k of n. So we get x minus y is equal to k prime minus k times n. You follow that?
Yeah.
Okay. So what did we just show? We showed x minus y is equal to some integer times n. That is the exact definition of x is congruent to y mod n. Their difference is a multiple of n. Or in other words, they have the same remainder when you divide by n. You did prove that this is logically equivalent to this. If x is congruent to y mod n, then x mod n is equal to y mod n. Right?
Yeah.
But what is x mod n? It's just x. X is already an integer in z sub n. X is in z sub n. When you modify n, it doesn't change it. It was already a remainder. It was already a number between 0 and 9, if we think about that z10. If you take a number between 0 and 9, and you look at its remainder when you divide it by 10, it's always just going to be whatever number you pick. If I pick 8, what's its remainder when I divide by 10? It's still just 8. So since x was already in there, then its remainder when I divide by n is still just x. Same thing with y. So x is equal to y, contradiction. Follow that proof?
Yeah.
Anything weird? Anything you don't like? Good? All right. So now we can have our definition of subtraction. Let n be a positive integer and let a and b be integers in Zn. Then we define b minus a to be x, where x is a unique solution to a plus x equal to b, namely b minus a mod n. Notice that's exactly what we defined it to be right here. So what is b minus a? It's b minus a mod n with regular arithmetic. Good? Is there anything weird about that?
Could you explain this b minus a mod n? I'm a little confused by that.
So let's look at two numbers. 13 minus, well, pick an m first of all. So what should we be in?
Z10.
Z10. Okay. So now let's look at 2 minus 8, something like that. How do we calculate this? Well, this is now the same thing, using what we just proved, as 2 minus 8 mod 10. Right? What is 2 minus 8
-6.
mod 10? 4. Remember, if it's negative, you can just keep adding n to it until you get positive again, if the negative's throwing you off.
What?
Oh, yeah.
-4 and 6 are the exact same thing, mod 10. Adding n, if I'm modding by 10, adding 10 to a number doesn't change the remainder. If I'm dividing a number by 10, adding 10s to that number doesn't change what the remainder is going to come out as. So when I'm modding by 10, if I add 10 to this thing, I didn't change the remainder. I didn't change what's going to be mod 10. I can add as many 10s to it as I want, and I won't change what the remainder is. So if it's hard for you to think about the number, -6, add 10 to it, 4.
So if it was each to the 12 and we came up with -6, that would just be 6 then?
Yeah. Just add 12 to it. Just add into it. Make it positive. Yep, perfectly valid to do. Any other questions? You need to see another example, or you think you got it?
Could we see another example?
Sure. Give me a number for z. 14. Give me the first number.
8.
Give me the second number. 16. So technically this is undefined, but we'll even do what we get this way. But technically you can't do this, right? Because this is not in there, but we'll do it anyways. So 8 minus 16 mod 14. Sorry, mod 14. What is that? What's 8 minus 16? Negative 8 mod 14.
So that's it.
Just 6. That's it. Okay. All right. Think you got it? Ready to move on? Okay. So that's our definition of subtraction. Okay. Now multiplication. Multiplication, we already know this last time, but let's renote it. So you know that in general, if I have a times b is equal to a times c, then that gives me b is equal to c with regular multiplication that you use in your algebra courses. But notice that that is not the case in the algebra that we're using. A times b equal to a times c in the arithmetic we're using, sorry. That product does not imply b is equal to c. Look at 2 times 3, what's that in Z10? What's 2 times 3 in Z10? 6. What's 2 times 8 in Z10? 16 mod 10 is 6. So these are equal mod 10, but 3 and 8 are drastically different numbers. There's no sense that they're the same number in this arithmetic, right? So just because this is true does not imply this is true in our arithmetic. Here's an example. And so this gives us a problem trying to define division. Because I know that this is 6 and this is 6. So if I try to do 6 divided by 2, what should it be? Should it be 3 or should it be 8?
Oh, that's right.
And it doesn't make sense to call it one or the other. We can't do it. Now, to help motivate how we are going to define division, let's go back to how we define division in good old regular arithmetic. In good old regular arithmetic, what was x divided by y by definition? It was x times y's multiplicative inverse, where y inverse is the multiplicative inverse of y. In other words, y inverse is the one and only number such that when you multiply by y, you get 1, the multiplicative identity. So, for example, if y is equal to 3, then what is its multiplicative inverse? Not negative 3. 3 times negative 3 is negative 9. We need the number, so when I multiply it, I get 1. The only number that does the trick is 1/3. That's why you were taught that 3 to the negative 1 is equal to 1/3. Similarly, let's do another one. What about if I want 5/2? Oops. 5/2. What's its multiplicative inverse?
2/5.
Just 2/5. You just flip the reciprocal, right? Okay, let's try another one. 0 times what equals 1? 1, right? 0 times 1 equals 1. No! 0 times 1 is 0. There is no number. Any number you put there, x, doesn't matter. This always comes out 0. So you can't divide by 0. It doesn't have an inverse. 0's multiplicative inverse is not defined. It doesn't have one. So 0 is acting similar to the way that 2 is acting over here. Not the exact same, but similar.
Like, wouldn't all numbers act that way, then? The way that 2 is acting?
Now, for example, if I'm in Z10, what's the unique number I can multiply 3 by to get 1? And the answer is 7. It's the only one. So then I could define dividing by 3 is multiplying by 7, or dividing by 7 is multiplying by 3. We define x divided by y to be x times its inverse. Now we'll define what we mean by inverse in our arithmetic, but it's motivated by this. We're going to do it the same way we do it here, kind of. We just need to figure out which numbers have this inverse. You notice that 0 doesn't have a multiplicative inverse in the regular numbers that you're used to dealing with. Turns out 2 doesn't have a multiplicative inverse in Z10. So not every number has a multiplicative inverse, so you can't divide by any number you want. There's only certain numbers you can divide by. Just like you can't divide by any number you want when you talk about real numbers. You almost can, there's only one exception there. In our arithmetic, there's going to be lots of exceptions. So we'll figure out when exactly you can divide and how to calculate that division. Okay, so let's get to talking about multiplicative inverses, or I guess he calls them reciprocals here. I'm probably going to say it's multiplicative inverse 100 times because that's what I'm used to calling it. Okay, so let n be a positive number, and let a be some number in Zn. With me so far? Okay, a reciprocal of a is an element b in Zn, it's some element in Zn, such that a times that element is equal to 1. So b is a reciprocal of a, since a times b is equal to 1. So if I can find a b such that a times b is equal to 1, then a has a reciprocal, namely that b. If a has a reciprocal, then we say that a is invertible. Now so far, for all we know, it could have a bunch of reciprocals. We didn't say that it only has one. We're just saying that this is what we mean by a reciprocal. A has a reciprocal if a times something equals 1. And if a does have a reciprocal, we're going to call it invertible. That's all we know so far, just definitions, and then we'll get to finding out when they do and don't have reciprocals. So to do this, I've written out this big multiplication table for mod 10. I didn't bother doing 0 because 0 times anything is 0. So I left out the 0 column and the 0 row because it would just be zeros. Outside of that, let's look at this multiplication table. So let's look at 1. Does 1 have a reciprocal element?
Yeah.
Yes, 1. What does that mean? That means multiplication by 1, or division by 1 is the same thing as multiplying by 1. It's its own reciprocal. It's its own multiplicative inverse. Same thing was true in the real numbers. If you take x and you divide it by 1, what do you get? Same thing when you take x and you multiply it by 1. You still just get x. Right? 52 divided by 1, 52. Same thing as 52 times 1. So 1 is its own reciprocal. Make sense? Okay. Now let's look at 2. 2 doesn't have a reciprocal. I can't multiply it by any number and get 1. There is no number I can multiply 2 by to get 1. 2 times 2 is, 2 times 1 is 2. Mod 10, 2. Oh, you're looking down here. What's 2 times 5? 10. Mod 10, 0. This is modular.
Okay, so only if it equals 1 then it's has reciprocal?
Yeah, that's exactly what this says.
Okay.
A reciprocal of A is an element B in Zn such that A times B equals 1. So, 1 is invertible because it has a reciprocal. 2 is not invertible because it doesn't have a reciprocal. Notice 3 has 1. What is 3 times 7? 21 mod 10 gives you 1, right? So 3 has 1. 4 doesn't, 5 doesn't, 6 doesn't. 7 has 1. Notice, since 3 was a reciprocal of 7, 7 is a reciprocal of 3. Right? If 7 times 3 equals 1, it better be the case that 3 times 7 equals 1 because we already said that this thing is
Well, that's so weird thinking about associative or commutative.
commutative. Okay, 8, it doesn't have any reciprocal elements. 9, notice 9 does. 9 is its own reciprocal element just like 1 was. So dividing by 9 and multiplying by 9 are the same thing in Z10. Doesn't change anything. Make sense? Should we prove that to ourselves real quick? So let's look at 7 times 9 in Z10. Sorry. Well, no, that's not going to be the case. All we can say is that times Z by 9 and divide by 9 are same. So we'll have to come back once we have a definition of division to see what I mean there. Sorry. Anyways, notice, can you notice a pattern between which numbers have reciprocals and which ones don't?
Odds.
5 didn't have one.
Well, I mean, the 1 and 9 did.
1 has one, 9 has
Prime
one.
numbers?
Like someone.
Which numbers?
Prime numbers?
Prime numbers? 2 doesn't have one and 9 is not prime.
Odd numbers?
5 doesn't have one.
Odd numbers except for 5.
Is this always the case? So it turns out that the numbers that are going to have these reciprocals are the ones that are relatively prime to the n you're talking about. Since our n in this case is 10, right, we're in Z10, these are all the numbers whose greatest common factor with 10 is 1. In other words, they have no common factors except for 1. What's the greatest common factor between 10 and 1? 1. What's the greatest common factor between 10 and 2? 2, not 1. What's the greatest common factor between 10 and 3? 1. What's the greatest common factor between 10 and 4? 2, which is not 1. What's the greatest common factor between 10 and 5? 5, which is not 1. With 6 it's 2, with 7 it's 1, with 8 it's 2, with 9 it's 1. So that's what it turns out is going to be the case. And we'll prove that. But you feel like you understand what this table is telling us? Okay. So now let's do a quick proof. We're going to prove that if A has an invertible element, or if A has a reciprocal element, then it only has 1. So it's impossible. You'll notice that each number only had 1. We're going to show it's impossible for a number to have 2. That's what this proof is going to be saying. Alright? So if A in Zn has a reciprocal, then it only has 1. That's what we're going to prove. So I'll let A in Zn and assume by way of contradiction that there exists B and C in Zn such that A times B equals 1, A times C equals 1, and B is not equal to C. Kind of a mouthful, but what we're saying is, assume that B is a reciprocal of A, C is a reciprocal of A, and they're not the same reciprocal. So we're assuming by way of contradiction that A has 2 reciprocal elements, namely B and C. You understand what we've said so far on line 1?
Yep.
It's a mouthful, but from here on out, it's pretty trivial. Okay. So then B is equal to B times 1, right? Which is equal to B times 1, right? That's a 1. Now, associativity, didn't change anything, just associativity, which is the same thing as 1 times C, which is equal to C. So B is equal to C. Contradiction.
That's cool.
Now, you are going to have to do a proof to show that A is equal to the inverse of A inverse. It is almost identical to this. You're going to show A is equal to A times 1 is equal to, substitute out a 1 for A inverse inverse times A inverse. Use associativity, cancel them out, and you're going to get that this is equal to this. So it's almost identical to that.
So we're going to prove it by way of contradiction.
No, this one you can just prove directly.
Okay.
Okay. Next definition. Okay, now we're ready for division. Let n be a positive integer and let b and z n such that b is invertible. Okay, so assume b is some invertible element. We just barely showed that if b is invertible, then it has one and only one reciprocal. Should have specified this before I wrote this. So from here on out, how will we designate b's reciprocal? We will designate it this way. Since b only has one reciprocal, now this is well defined because it references one and only one number. What is b inverse? It is b's reciprocal. If b is 7, b inverse is 3. If b is 1, b inverse is 1. If b is 9, b inverse is 9. It's its reciprocal element. of b. Make sense? Okay, so here's our definition of division now. So for any a and zn, we define a divided by b to be a times b's inverse. Notice this is exactly what you're used to in thinking about regular numbers. If I say what's 4 divided by 3, you can think about that as 4 times, what's 3's reciprocal? 1/3, which gives you 4/3. 4 divided by 3 is the same thing as 4 times 1/3. By definition, that's what 4 divided by 3 is. It's 4 times 1/3. Make sense? Or 4 times, to use the same notation we have it there, 3's multiplicative inverse. Okay. So, a divided by b is defined to be a times b's multiplicative inverse. Let's do some examples. In Z10, what is 2 divided by 7? It is 2 times 7's multiplicative inverse. What is 7's multiplicative inverse in Z10? 3. So it's the same thing as 2 times 3, it's 6. So 2 divided by 7 is 6.
And if it does a number that you can't divide by, then it's undefined.
Yeah, you can't do this if the number you're trying to divide by doesn't have a multiplicative inverse. Same reason you can't divide by 0. It doesn't have a multiplicative inverse.
So in this case, 2 divided by 6 wouldn't work.
Yeah, you cannot do 2 divided by 6. Undefined.
Why is that?
Huh?
Why is that?
Because it gives multiple things. There's multiple solutions, or there's no solution is typically what we mean by undefined. Think about what it means to define something. It means to say exactly what it is. It's this one and only one thing. If you were to go to a dictionary and you were to look up a word and it says, well, it's either this thing or it's this other thing, that doesn't really tell me what it is. Which is it? So a definition needs to refer to one and only one thing. That's what we mean when we say something is well defined. So that's why I was stressing so much before, over here, the fact that if something has a reciprocal, then it only has one reciprocal. So now this symbol is defined because it references one and only one number. So if b has a reciprocal, then it only has one. And so this references one and only one number, so the symbol is well defined. Okay. Another one. If we try to do 2 divided by 3, what is that? That's the same thing as 2 times 3's inverse, which is 2 times 7, which is 4. So 2 divided by 3 is 4, and 2 divided by 7 is 6. Right? Feel like you could calculate some of those on your own? Let's just throw some other ones in here and not use Z10 for a second. Let's use Z11. And we'll look at, what should we do? 3 divided by what? You want to do 7? We can do 3 divided by 7. That's fine.
Does 7 have an inverse in Z11?
What's the greatest common factor between 2 primes? 1. So yep, we're guaranteed. In fact, the fact that we chose an 11 there means almost everything works.
With the exception of
0.
oh.
So, what is 7's multiplicative inverse? What is 7 inverse? What number times, when we use this times, 7 is equal to 1?
It's not 3 anymore. It's 4.
No, it's not 4.
It's 4.
No, it's not 4. 4 times 7 is 28. Mod 11 is 6.
I'm adding
It's 8.
It's 8. 8 times 7 is 56, which is 1 more than 55, which is obviously a multiple of 11.
Oh my gosh.
That's how you find these really quick.
That is
You just
not-
start counting by 7 in your head until you're 1 over an obvious multiple of 11.
Okay, wait.
7, 14, 21, 28, 35, 42, 49, 56. 56! Oh, that was 8. Okay.
How is 7 times 8?
Okay, let's look at it. 8 I guess we wrote that way, but yeah, we'll do this. 7 times 8 is equal to 56 mod 11. How many times does 11 go to 56? With the remainder of? Boom. She's got it. It's equal to 1. So, 3 divided by 7 is equal to 2, right? What? 3 divided by 7 is 3 times 8. What's 3 times 8? 24 mod 11. 2.
I was like, no, you're messing with us.
That's what homework's for. And just so you know, you don't only have to do the homework problems. You can do more problems.
Oh.
I won't dock you for that. If you turn it in, I'll dock you. I don't want to look at it. And the author, by the way, does give answers to a lot of problems in the back. So you can also look at the ones that he gives answers to, then go solve them and see if you get the same thing. That's the point of the solutions in the back of the book, in case you didn't know. It's like you can go try solving it all on your little lonesome and check your own work. You don't even have to have me there. It's crazy. It's like kids can learn on their own. All right. We don't need to erase that. Doesn't matter. Next, let's see what we're doing now. Let n be a positive integer and let a and z n. Then a is invertible if and only if a and n are relatively prime. Okay, here's the big one. So we've kind of been assuming this whole time. Now we're going to prove it. So now you know for sure if a and n are relatively prime, then they're inverses of each other.
What does it mean to be relatively prime?
Or if they're relatively prime, then a has an inverse. Their biggest common divisor is 1. Their GCD is 1.
Okay. Isn't that a lot of work just
That's
to
all
figure
prime
that out?
numbers.
A lot of work.
Yeah.
No, you're going to see how extended Euclid's automatically gives you the inverse for free. So what you were doing, you were already calculating the multiplicative inverse of numbers. You were already doing it. You just didn't know you were doing it. We're going to show you that you were doing it. Okay? So you were already figuring out how to find the multiplicative inverse. So when I say, what's the multiplicative inverse of 29 in Z431, you already calculated that. And now I'm going to show you how you already calculated it. Okay. Yeah. Anyways, back to this proof. This proof's the heart of this whole section, so let's go over it. So let n be a positive integer, let a and z n. Then a is invertible if and only if a and n are relatively prime, or in other words, if their GCD is 1. Good? And remember what we know about numbers when their GCD is 1. If I have two numbers, I know that their GCD is 1. So if I have two numbers a and b, and I know that their GCD is 1, then I know that there exists x and y such that this is true. Oops. So if the GCD of a and b is 1, then I know that there exists x and y such that this equation is true. We proved that last week. So remember that because we're going to be using that. Told you that that was the second most important theorem in number theory. Remember that? I'm trying to stress that. Okay. In the number theory that we covered. That's what I mean by most important. We're here. Nice, easy, straightforward proof. Assume that A is invertible. We need to use that fact to show that A and N are relatively prime. So go in this direction first. This is an if and only if. We're going to show that if they're invertible, then A and N are relatively prime. And then we'll come back this way, show that if A and N are relatively prime, A is invertible. So assume A is invertible. Then, what is A times its inverse? 1. So what does that mean? That means A times its inverse mod n is equal to 1, right? Plugging in the definition of this multiplication. What is A times A inverse? That's A times A inverse mod n. That's how we define this multiplication. And this gets us back to regular multiplication, right? This is definition of multiplication. I know that's equal to 1, so it's equal to 1. Good? Now, if this mod n is equal to 1, 1 is equal to this times some plus some integer times n. So we're going to do that a lot. We're going to go from things that look like this to things that look like this. This side a times a inverse mod n is the same thing as a times a inverse plus some integer times n. And we know that's equal to 1, so it's still equal to 1. Good? All right, notice what we did. We now have a times some integer plus k times some a times some integer plus some integer times n equals 1. Therefore, using the theorem we proved last time, the GCD of these two numbers is 1. Just so happens the GCD of these two numbers is also 1, and the GCD of these two numbers is also 1, and the GCD of these two numbers is also 1. But all we were trying to prove is that the GCD of these two numbers is 1. Two numbers are relatively prime if and only if I can express them like this. That's a proof that we already did. So, since I can express them like that, then their GCD is 1. Ta-da! Now the next way, which is basically just as easy. Assume that a and n are numbers such that their GCD is 1. So assume that a and n are relatively prime. Their GCD is 1. Same thing. Now I need to show that a is invertible. And this is going to show you how you actually calculate the a inverse. It's reciprocal. So assume a and n are numbers that are relatively prime. Then, same thing up here, then there exists x and y such that ax plus ny equals 1. Right? Two numbers are relatively prime, they can be expressed this way. Now, I'm just going to rewrite this with the ax. I'm just going to move the n times y to the other side. So I get a times x is equal to an integer times n plus 1. Right?
Why?
Well, now, notice, what is a times x mod n? 1. When I take a times x and I divide it by n, my quotient is negative y and my remainder is 1. I have a times x written as an integer times n plus a number between 0 and 1. Or 0 and n. So, a times x mod n is 1. So, x is a's reciprocal. You see that?
I think so. That's kind of mind-boggling. That's kind of
You
cool.
need to get comfortable with this theorem up here if you're going to have a stand a chance with understanding number theory. You need to understand this one, and you need to understand this one. That when we divide, that's the same thing as this. Any questions about that proof? I recommend you read it and read it again until it makes sense. And if the theorems that I'm choosing don't make sense, go back and reread those. These basic theorems are the ones that you need to understand for number theory. The dividing theorem, the one about expressing ax plus yb as 1, and those two. Those were the big ones. Okay, so now let's go through an example where we calculate 29's inverse in Z 431. Now you could start going through and saying 29 times 1 and modding it by that and seeing if you get a remainder of 1. And then you can plug in 2, and then you can plug in 3, and then you can plug in 4, and then you can plug in 5. And you could do it that way. But that's a really tedious way to do it. Instead, we're going to show you how to calculate it doing things that you've already been doing, just Euclids, extended Euclids. So first I'm going to find your GCD. I know their GCD is going to be 1. That's not the point. The point is I'm going to be using extended Euclid, so I need to go through the algorithm. So 431 is equal to 1429 plus 25, right? Just find the GCD. Now, I'm going to write 29 out. 29 is equal to 125 plus 4. Do you remember going through this algorithm? Anyone confused by what I'm doing here?
No.
And then, now we have the 25 and the 4. Rewrite it over here. 25 is equal to 6 fourths plus 1. Okay, we got down to our GCD 1, right? Now we come over here, solve for the remainder in each case. 1 is equal to 25 minus 6 24s. 4 is equal to 29 minus 125. 25 is equal to 431 minus 1429s. That's all I have written here. Good? Now I'm going to find the x and y such that 1 is equal to x times, what's my number? 431 I'm going to write 1 is equal to x times 431 plus y times 29. This is what I'm trying to find solutions to, right? And you've already done this. You're given problems like this, and you're told find x and y's that give me solutions. Notice, just even ignoring this for a second, just notice that once we have this, how we get our inverse. Because now, look at it. When we mod by 431, what's this number? 0. What's the remainder of a multiple of 431 when I divide by 431? 0. What's the remainder of this thing? Has to be 1.
Wait, what?
Yeah, why is that?
Mod both sides of this equation by 431.
Oh.
What do I get on the left side? 1. What do I get on the right side? 0 plus something that has to be 1, because this is an equation. It's an equation, don't lose track of that. So this, mod 431, is going to be 1. So the y that we get here is going to be our multiplicative inverse. Or at least a multiple, some multiple of 431 away from our multiplicative inverse. And y mod 431 will for sure be our multiplicative inverse. So y might turn out to be some really massive number, but when I mod it by 431, it will be our multiplicative inverse. That's all we're going to be doing. So once I write it this way, it's really easy for me to calculate the multiplicative inverse of 29. It's just whatever that number is, mod 431. That's what we're going to do here. So here we were finding the GCD. Here we're using extended Euclid's, right, in terms of the remainder. Now I need to write 1 in terms of 431 and 29. Well, I have 1 in terms of 25 and 4. Substitute the 4. So this substitution for 4. And now, collect like terms, and now I have 1 in terms of 25 and 29. Substitute the 25. And now I have 1 in terms of 431 and 29. Like I wanted. So here is the multiplicative inverse of 29. Negative 104. Now, negative 104 isn't in the range that we want, so I just need to mod it by 431 or add 431 to it. And that will be my answer. So this gives me, I'm just making it abundantly clear. Okay, now I know that this mod 431 is equal to 1, or is equal to 1 mod 431, which is still just 1. Right? And now I know that negative 104 mod 431 is equal to 327. How did I get that? Just add 431 to negative 104, and you get 327. Okay. So, 29's multiplicative inverse is 327. Or in other words, I now know that 29 times 327, using that times, is equal to 1. You can plug that in on your calculator. Take 29, multiply by that, divided by 431, so your remainder is, it's going to be 1. Make sense? So now that we have 29's multiplicative inverse, we can figure out something like 30 divided by 29. And what is 30 divided by 29?
30 times 327.
This is equal to 30 times, this type of times, 327?
Yeah.
327. And 30 times 327 is obviously, I don't know either. A big number, right?
Not mod 431.
Mod 431, yeah, because we use that circle times. Because we're still here. So this is the same thing as 30 times 327 mod 431, which comes out to whatever it comes out to. Point is, you can calculate that, right? Okay. And that's the end of that. So now you know how to divide in Zn. It's not trivial at all, but now you know how to do it. Okay, next we're going to move on to finding solutions to equivalence. Equivalences mod 11. We're going to be solving systems of equations like this, in other words. Shifting gears here a little bit. So if I tell you that x is equivalent to 4 mod 11, what are all the possible numbers x that satisfy this? Give me one that satisfies it. Do you remember these at all?
No.
We did these forever ago.
Like x minus 4 mods.
X is congruent to 4 mod 11 if and only if they have the same remainder when I divide by 11. You did a proof with these just not that long ago.
Yeah.
You just barely proved that x congruent to y mod n, I don't know what variables you use, is logically equivalent to x mod n equals y mod n. You just did this. Mod n. You remember doing that proof?
Yeah.
That congruence is exactly what we're talking about here.
I thought there was a difference if mod 11 was in parentheses and not parentheses.
There is. Oh, sorry, I should have parentheses here. We use the parentheses when we're talking about a congruence, so you know that it's not an operation. Here, mod is actually an operation, the same way plus is an operation. This one over here is the same mod you use in computer science all the time. That little, you use a percent operator. That's exactly what that mod is. That's not what it is over here.
Right.
Over here, we're saying if you were to mod this and this, then you would have the same thing, which is exactly what that's saying. Right? So, back to my question. Give me a number that is congruent to 4 mod 11.
50.
50?
15.
15. What's 15 mod 11?
4.
4. Yep, it works. Give me another one.
26.
26. She keeps making it harder. 26 mod 11 is 26 when you divide it by 11. How many times does 11 go into 26? 2 times with the remainder of 4. What's the easiest solution to this? 4. 4 is congruent to 4 mod 11, right? There's a very straightforward solution. And we could also get a negative solution. Give me a negative number.
Negative 7.
Negative 7. What's negative 7 mod 11? If you can't do it, keep adding multiples of 11 to it until you can. So negative 7, we don't know how to deal with that. Add 11 to it, we get 4. Is 4 congruent to 4 mod 11? Yes. Okay, so you see how this has infinitely many solutions, right?
Yeah.
In general, all its solutions are of the form x plus 11 times k. Oops, not x, 4. 4 plus 11 times k. All the solutions are of this form. Take any number of this form, plug it in for x, it's going to be true. Does that make sense? So pick a k, any k.
5.
5. Plug in 5 for k, you get 55. 55 plus 4 is 59. If you were to do 59 mod 11, you'd get 4. Does that make sense? So we're looking for all the solutions to equations like this. So now let's do another one that's not as trivial. I want to find all the x's that give me solutions to this equation. Oh, and I want to make a note. From here on out, so I'm not writing mod 11 over and over again, we're just going to do parentheses 11 like that. So now we're going to solve 3x is congruent to 4 mod 11. Okay? We're trying to solve for x. We're trying to find all the solutions of x that make this true. Once we find one solution, finding all the other solutions is easy. Just like once we knew 4, we knew 4 plus 11k was all the answers. Similarly, this is also true. We could have done 15 plus multiples of k. When k is negative 1, that gives you 4. So once you have one solution, adding multiples of 11 gives you all the solutions. Make sense? So let's solve this thing. So 3x is congruent to 4 mod 11. Let's see, I want to get x by itself. How do I get rid of the 3? I need to divide by 3, which is the same thing as multiply both sides by 3 inverse. So then I know 3 inverse times 3 times x is congruent to 3 inverse times 4 mod 11, right?
Yeah.
And what is 3 inverse?
1/3.
No, and no. We're in mod 11.
It's 8.
It's 8/2, so close.
Yeah, so it's 4.
So it's 4. Wonderful. 3 inverse is 4. What's 3 times 4?
12.
12. Is 12 one more than a multiple of 11? Yup. Okay. So, what's 3 inverse times 3? 1. Don't hurt your head plugging in 4 and then modding it. By definition, 3 inverse times 3 is 1. Keep it easy. So 1 times x is congruent to 4 times 4 mod 11 is 5. Did you count my fingers?
Well, you could have just gone 3 times what? You could just leave fraction symbol for bonds.
Notice that we are talking about, we're in this congruent, so we're just using regular math.
But we're not.
4 times 4 mod 11.
So,
Yeah, you did that weird, bro.
what did I do weird?
3.
4 times 4 is
60.
mod 11.
Okay.
Okay. What?
Why can't you just go, what's 3, 15 divided by 35?
Say that again.
15 divided by 35.
Where are you getting a 15 from?
From the one on top.
From up here?
Yeah.
We're not talking about the same one.
Okay.
This problem has nothing to do with this problem.
It technically
Oh, okay, they were related. The fact that they were related was an accident.
There, you can just think that.
You could. You can use your past knowledge to solve future problems. That's 100% correct. And yes, you could have thought, well, I don't know the x that gets me to 4, but then add a multiple of 11, we didn't change anything, 15. Okay, now I know the x that gets me to 15. You could have thought about that way if you want. That's going to be in general harder, but you can't think about it that way.
Not hard.
It's easier in this case. Do it for these cases. Well, you don't know how to do the system yet, so ignore that for a second. Let's stick with this. Okay, so now what Emma's saying is, hold on, we're basically treating this thing like an equation. It's a congruence relation. That's not the same thing. Notice behind the scenes, we're kind of cutting corners here because we don't want to do this every time. But we could have started with 3x is congruent to 4 mod 11. That's the same thing as 3x mod 11 is equal to, and now we're using equals in the normal sense of the word, 4 mod 11, right? And now I can do my modular arithmetic that I'm used to, and then convert it back this way. In other words, I can redefine this now as 3 times x using our modular arithmetic times, and this as just 4, and then multiply both sides by 3 inverse, viewing it in the mod, and then undoing and coming all the way back to here, which is very tedious to do that. So you can do your modular arithmetic here, the same way you expect, and you'll be fine. But you don't even have to think about that 3 inverse that way if you don't want to. You could have just flat out said, I don't want to think about it that way. I'm just going to multiply both sides of this by 4, which I know is valid. Because we have the same numbers on both sides, the same number times 4 is still the same number. And you could have thought about it that way and never really resorted to using that 3 inverse notation if you don't want. Make sense?
Somewhat.
Somewhat. You feel like you could have solved this? Do we need to do another one? Should we do another one?
Can we do another one?
Yeah. Give me some numbers. 5x congruent to
6.
congruent to 6 mod what?
8.
Mod 8. All right. We're going to find 5x congruent to 6 mod 8. Now Rhoda's going to start plugging in 8s to that, and she's going to figure out that way. What are we going to do?
Find the inverse of
We're going to find the inverse of 5 mod 8. Okay? So what is it?
2.
3. It's 3.
Okay. 3 times 5 is 15, mod 8 is 7. So no.
Wait, what?
Keep
No,
counting
sorry,
by 5.
It's 5.
It's
I
5.
see
25 is
eight.
1 more than 24, which is a multiple of 8.
Okay, wait.
What is 5 times 5? Divided by 8. What's the remainder? 8 goes into 25 3 times with the remainder of 1.
Yeah, you might just do 5.
Huh?
Like I was thinking one, but I didn't want to see that because it sounded like it was
So, multiply both sides of this by 5's multiplicative inverse, which is the same thing as 5. So then, I have 5 times 5 times x is congruent to 6 times 5 mod 8. Right?
Why are you trying to do by 5?
Because, what is 5 times 5?
25.
Mod 8.
But why did you start with that?
This was the equation that we're solving. I multiplied both sides by 5, which is 5's multiplicative inverse. Okay, maybe I'll write this.
Oh, okay, that's what I'm looking for.
Okay, there we go.
Okay.
Now, this is,
That's
oh, the whole thing is x. This is 1, so the whole thing over here, yeah, is x, is congruent to. Now, 6 times 5's inverse is the same thing as 6 times 5 is 6.
30.
30 mod 8. 8 goes into 30 3 times with the remainder of 6. Right? So, x is congruent to 6, so all our solutions now are x equal to 6 plus any integer multiple of 8, k times 8. These are all our solutions. Pick any k you want. 1. Okay. What is 8 plus 6? 14. Plug 14 into this equation, what do we get? Let's do the math. What's 14 times 5? Hint, 7 times 10. 70. Now we're going to mod it by 6. Oh, sorry, by 8. Thank you. So over here, when we plug in, what were we plugging in? 14. So then we got 70 is congruent to 6 mod 8. Let's see if that's true. 8 times 8 is 64. So 70 divided by 8 is 8 with the remainder of 6. Yep, it worked. Right? Do a bunch of examples. Okay, sorry. That doesn't make sense when you catch up?
Are you saying that is
If you catch up? I'm saying all the solutions look like this. Pick any integer k you want, you'll get a number out. Plug that number in for x up here, and the equation's true. Notice this has infinitely many solutions. All the solutions look like this. 6 plus some integer multiple of 8. Because adding multiples of 8 is going to change it. Yeah, if I say, find all the solutions to this equation, here are your solutions. I mean, you can be very explicit if you want. You can say it's a set of all 6 plus k times 8, where k is an integer. Okay, here's a set of all solutions, if you want to write it that way. I'll be content if you just say it's 6. But
Okay, but that's
expand
for
this set out.
So you put a number in for k, and you get an x. And then
Pick an integer, any integer you want. Evaluate this expression. It's a solution to this equation. The equation has infinitely many solutions.
Okay, so that would be our solution. Is
Yes.
that equation?
You could write it this way if you want. You can say it's a set if you want. Whatever makes more sense in your brain. Huh? Got it. Okay. Now let's do one a little bit more interesting. We now have 2 equations. So I want to find all the x's out there that are solutions to this and this. They satisfy both equations. I want all the numbers out there such that when I divide it by 7, I get a remainder of 1, and when I divide it by 11, I get a remainder of 4. You with me?
You're saying there's more than one solution?
Yeah, there's infinitely many. This isn't like 2 intersecting lines. So, let's find it. First off, what are all the solutions to the first one?
It's all the numbers that can be written as 1 plus an integer.
Since x is congruent to 1 mod 7, that gives me that x is equal to 1 plus some integer multiple of 7. Right? Solutions to the first one. Really simple.
So, wait. You didn't have to do that because it's just 1 side. Right?
Yeah, we didn't have to do any math. Over here, the only math we had to do was to get x by itself. This should have been x.
Okay, but that 6 and that 6 are not the same 6, right?
This 6 and this 6?
That 6 and 1 on top.
This 6 and this 6?
Yeah. They're not the same, right?
They are not the same. That was a coincidence. Good catch. Okay, so I know if x is congruent to 1 mod 7, or in other words, if I know that x is a number such that when you divide it by 7 to get a remainder of 1, x has to be a number of this form. It's an integer multiple of 7 plus 1. Right? That makes good sense? Okay, now I also know that x is congruent to 4 mod 11. Which means that x is congruent to 4 mod 11. You with me? All I did is substitute what I know x is. This is going to give me some restriction on k. And I'll get k in terms of some other integer. Substitute back in, and I'll get x in terms of some other integer, and we'll be good. So, now we just need to solve this for k. Easy as pie, right? So 7k is congruent to 3 mod 11. Right? Subtract 1 from both sides.
Can you do normal math?
Can you do normal math? Yeah, you can do normal math. Remember that these are just equations behind the scenes.
Yeah.
Or, I have a number here, I have a number here. When I subtract 1 from those numbers, I still get the exact same number. However you want to think about it. Yeah, we can do normal math. Okay, so now, what do we need to find? We need to find 7's multiplicative inverse mod 11. We've already done that one today. It's 8. 7 times 8 is 56, is 1 more than 55, is a multiple of 11. Right? Okay. Let's do it. So multiply both sides by 7's inverse, namely 8. So 8 times 7 times k is congruent to 8 times 3 mod 11. Which gives me that k is congruent to what? 2. Anyone going to argue with that?
Wait.
All right, we'll wait.
8 times 3 is?
You tell me.
It's 2.
Okay. It's 2 mod 11. Okay? So that means, what does k look like? K is equal to 2 plus some integer, we'll call it j, multiple of 11. Right? If k is congruent to 2 mod 11, then all the integers k that satisfy this are of this form, where j is just some integer. I just picked some different number or variable j to represent our integer. So now I know what k is. Come plug that back in for x, because remember, we're trying to figure out what x is. So now x is equal to 1 plus 7k, which gives us that it's equal to 1 plus 14 is 15, plus 7 times 11 is 77. 77j. So now what am I saying? I'm saying that x equal to 15 plus any multiple of 77 you want satisfies both these equations. The smallest number that satisfies them is 15. Plug in 15. 15 divided by 7 is, the remainder of 15 when you divide by 7 is 1. The remainder of 15 when you divide by 11 is 4. So 15 satisfies both those. Okay. And notice that 77 is a multiple of 7, and 77 is a multiple of 11. There's no accident that this is a product of those two things. So adding 77 to this number doesn't change it mod 7, and adding 77 to this number doesn't change it mod 11. So 15 is a solution, and when I add a multiple of 7 to it, it's still going to be a solution to this. When I add a multiple of 11 to it, it's still going to be a solution to this. Therefore, when I add a multiple of 11 times 7 to it, it's still going to be a solution to both. And that's how you solve a system of equivalences. I think they're called congruences. Modular congruence, is that what it was? I keep saying equivalence, I don't know why. But there. So you're going to have to solve the system of those equations. I give you 3 of them on the test, and you have to solve the system of all 3 of them. To solve 3 is the same as solving 2. Once you solve these 2, you could easily just solve another one now. Plug this in for x, solve it, and you'll get it in terms of some other integer n, whatever you pick.
Do we do 3 on our homework?
I don't know. I don't really know if you do 3 on your test. I just wanted to be scared enough that you're paying attention. Okay, so that is solving systems of modular congruences. Good? All right. Now we're moving on to the fundamental theorem of arithmetic. The fundamental theorem of arithmetic. What does the fundamental theorem of arithmetic say? It says you can represent any positive number as a product of prime factors. Yeah, obviously.
What was that?
This is super fundamental to arithmetic.
Is normal arithmetic?
Yes. Normal arithmetic. We're in a new section now. We're not in modular arithmetic anymore. So, fundamental theorem of arithmetic, you can represent any positive number as a product of prime numbers. Whoa, wait a second. What about 1? What's the prime factorization of 1?
1.
1 isn't a prime number.
Oh.
Yes, with the exception.
1 is the empty product. Same reason that 0 factorial equals 1. 1 is the empty product. And it makes perfect sense to make 1 be the empty product, just like it makes perfect sense for 0 to be the empty sum. Imagine for a second that I had a bunch of numbers I was trying to multiply together. 19 times 13 times 27 times 16 times 5, whatever. And I don't want to multiply them all in one go, but instead I want to multiply this group together and then this group together and then just multiply my groups together. That's perfectly valid, right?
Yeah.
So I say, Peter, I want you to multiply these ones. Emma, I want you to multiply these ones. And Laura, I want you to multiply these ones. And then I'll take your answers and I'll multiply them all together. Peter's going to give me that product. Emma better give me a 1, otherwise we're screwed. And Laura's going to give me the answer to that one. If Emma gave me a 0, uh-oh, we're going to get 0 as our whole solution. The empty product is 1. Another way to think about it, if I tell you 7 squared, what's 7 squared? That's 7 times 7, 2 times. So that comes out 14. Okay, what's 7, 0? That's 7 times 7 times 7, 0 times.
7 squared is 14.
Which is 1. The empty product of 7s is 1.
Yeah, I think you're confused.
You said 7 squared.
7 squared was 14. That's what
Oh,
I said.
sorry. 7 squared is 49. 7 times 7. Yeah, I was adding in my head. 7 squared is the same thing as 7 times 7. 7 times 7, 2 times. 7 to the 0, if you want to think about it that way, is 7 times 7 times 7, 0 times, which is 1. The empty product of 7s is 1. So an empty product is 1. What's the prime factorization of 1? The empty product, which is 1. That's its prime factorization. Good?
Just emptiness?
The empty product.
Just nothing. Like that's its prime factor.
Not nothing, the empty product.
Which is 1.
So the prime
And
factor-
you have to know that you're applying a product to an empty list if you want to think about it as applying it to a list of numbers. Or when we define this product, we use pi for product. The product from I equals 1 to 0, or from 0 to 0 of I, that was 1, an empty product.
Alright.
So an empty product and nothing are not the same thing. Okay, so 1's the only number that might make you scratch your head and look at that. If you got 1, I think everything else makes perfect sense and you're good to continue. 1's the only gotcha, in other words. Okay, so let's actually read the theorem now. Let n be any positive integer. Then n factors into a unique product of primes up to their order. What do I mean by up to their order? The unique prime factorization of 30 is 5 times 3 times 2. Now you can write that in any order you want, but it's uniquely 5, 3, and 2. 1, 5, 1, 3, 1, 2 are what make up 30. I don't care the order you write them in. 12's unique prime factorization is 2 2's and a 3. I don't care what order you put it in, its unique prime factorization is 2 2's and a 3. Make sense what we mean by unique up to their order?
Yeah.
So ignoring order, that's a unique factorization. That's what we mean. So fundamental theorem, pick any number out there that you want. I can represent it as a product of prime numbers. And a unique product of prime numbers. So two different numbers can't have the same product factorization. Otherwise they'd be the same number. Okay. So this should all be pretty intuitive stuff that you've already come across, but now we're going to explicitly prove it. Because proving it isn't trivial. Okay. No, one is the empty product. We already talked about that. Okay. So let's do our first proof leading up to proving that theorem. That theorem is going to be what we prove close to the end, but we got to work our way up to it. So first thing we want to prove, let A, B, and P be integers. We're not in Zn anymore. These are just regular integers. Good old-fashioned arithmetic. So let A, B, and P be integers where P is prime. If P divides the product of A and B, then either P divides A or P divides B. Make sense?
Makes sense.
Could it divide both?
It can divide both. If this is true and this is true, then this or this is still true. What does it take for an or to be true? One of the statements at least has to be true. They can both be true. So or the exact same way we use it in logic. Any other questions so far? Okay, so let's prove it then. So 1, let A, B, and P be integers such that P is prime and P divides A and B. A times B, I should say here. Assume by way of contradiction that this statement is false. Now what is the false of this statement? It's this statement. Assume by way of contradiction that P does not divide A and P does not divide B. Remember that not A or B is the same thing as not A and not B.
Yeah.
So if it's not this or this, then it's not this and not this. Not and not. Follow that?
Yeah.
Okay, so this is a contradiction of that. So assume by way of contradiction that P doesn't divide A and P doesn't divide B. Since P is prime, its only positive divisors are 1 and itself. Right? A prime number. What are the divisors of a prime number? Plus or minus 1, plus or minus a prime number. Well, we said positive divisors, so just 1 and P. Those are the only positive divisors of P. Good?
Yeah.
Okay. Then, since P does not divide A, so in other words, P is not a divisor of A, then the GCD of A and P is 1. Does that make sense?
Yeah.
P's only positive divisors are 1 and P. We know that P is not a divisor of A, so the only other divisor that A and P can have in common is 1. So the GCD of A and P is 1. Make sense? Similarly, the GCD of B and P is 1. Exact same logic. With me so far? Now we're going to use that theorem that we love so much. Up there, AX plus BY equals 1. Since the GCD of these two is 1, then there exists X and Y such that AX plus PY equals 1. Also, since the GCD of B and P is 1, then there exist integers, we're calling them W and Z, such that B times W plus P times Z equals 1. You follow me there? Okay. So now, we're going to multiply 1 by itself and see what happens. So then 1 is equal to 1 times 1 is equal to 1 times 1. It's the biggest one I've ever seen. All right, let's make it bigger. Multiplying this out, AX times BW is ABXW. Those two is right there. Those two are right there. Notice I put the P first on purpose. I put the AB first here. I put the P first here. Those two, what? Did I mess up?
Yeah. You pointed to the two outsides, like, and then.
Okay, so I did this one. Oh, and then I did this one.
Inside.
Okay, so I did these two is my first term. These two are my second term. right?
Yeah.
And then these two are my third term.
Yeah.
And then these two are my fourth term.
Mm-hmm.
Notice that we have P divides AB, so this is a multiple of P. This is a multiple of P. This is a multiple of P. And this is a multiple of P. So this, and this are all multiples of P. In other words, I can factor P out of this whole thing. So 1 is equal to P times an integer. Or in other words, P divides 1. Obvious contradiction. P is a positive number bigger than 1 that divides 1. No, contradiction. That's impossible. Okay. Follow me there? So, therefore, P divides A or P divides B. Good? Okay. Now, I think I did a homework problem for you guys, which is this problem, which is a nice little inductive proof to make sure that you didn't forget how to do proof by induction. Alright, here's what we're going to prove. Let P and Q1, Q2, Q3, Q4, all the way up to Qn all be prime numbers. Okay? Just a bunch of primes. We got P and then n other prime numbers. They might be the same, they might be different, all we know is that they're all prime. What are we going to prove? We're going to prove that if P divides their product, then one of those prime numbers had to be P. So if P divides a product of prime numbers, then one of the prime numbers in that product has to be P. So now let me say it using what we have right there. If P divides this product, then there exists a term in that product such that P is equal to that term. Notice that this is Q1, Q2, Q3, all the way up to Qn. So whichever one P is equal to is going to be Q sub I, where I is between 1 and n. All this whole thing right here is saying is that P is equal to one of these products. Don't get confused by the little I there. Is the little I throwing anyone off? No. Okay, I think it's pretty straightforward, but I know it's a lot of notation, so. Saying something very simple with a lot of notation can sometimes be confusing. So, proof by induction. Base case. Observe that if P divides Q1, so base case is when there's only one Q. So I'm going to show it's true when there's only one Q, assume it's true when there's K Qs, and show that implies it's true when there's K plus 1 Qs. Proof by induction. Right? Proof by induction. Behind the scenes, what are we showing? Oh, I didn't move the camera.
Oh.
Well, sucks for you guys. You missed all that stuff. Rhoda, your one job.
Oh, sorry.
I don't think you are. You will be when you try to do your homework.
What?
You have homework? Yes, you have homework. Jeez. Good enough. All right. So, the proof by induction. I need to start just leaving a note at the top of every whiteboard saying move the camera. Huh.
It's only recently that you've been forgetting.
Yeah, I need to caught up on what we're doing.
This is the only time you're not.
In my topology, he forgets a lot. So.
No, I've forgotten this class before. Last year watching the lectures.
Huh? Oh.
All right. Okay, let's proof by induction. So, how do we prove proof by induction? What are we doing behind the scenes? We're trying to show that, we'll erase right here and just write it here. We're trying to show two things. We're trying to show 1 is in A, and then we're trying to show if K is in A, that implies K plus 1 is in A. Therefore, A is all the integers, or all the positive integers. Right? And so we typically say, let A, I can't remember if we use an A, I just wrote an A over here. Let A be the set of all the integers that make this statement true. We show 1's in there, we assume K's in there, we show K plus 1's in there.
Yeah.
Typically, when you actually go do proof by induction, it's so obvious that this is what you do behind the scenes that you ignore referencing the set A. You just show, I'm going to show that the statement is true for 1, I'm going to assume it's true for k, so that implies it's true for k plus 1. Same logic though. So, show that this is true in the case where n's equal to 1. Well, with n's equal to 1, in other words, if I only have one of these cubes, that looks like this. So, base case, observe that if p divides just one prime number, p is equal to that prime number.
Yep.
Right? The only positive divisors of this is 1 and itself. This divides it, it's not 1, so they have to be equal. Alright, that's the base case. Now, assume for n equal to k, assume this, and show that implies this. Assume for n equal to k that if p divides the product of k primes, then there exists one of these primes such that p is equal to it. And that little q sub I is obviously between 1 and k, because there's only k of them. It's equal to at least one of them. Maybe the same prime number showed up a lot, but it's equal to at least one of them. Right? So assume that that's the case. So then we have, assume p divides k plus one of them, and we need to show that p is equal to one of them. Right? So assume p divides the product of k plus 1 integers, or k plus 1 prime numbers. Notice that I can rewrite that as p divides the product of the first k times the k plus 1. Right?
Yeah.
I'm just grouping. I'm grouping these ones together and leaving that one all by its little lonesome. Yeah, that's very sad. Now, notice what we said over here. If p divides a product of two things, then p divides the first thing or p divides the second thing. So I have p divides a product of two things. Right? So then I know, by the previous proof, that p divides the first thing or p divides the second thing.
Okay.
Well, obviously, if p divides the second thing, p is equal to that second thing, in which case we're done.
Okay.
If p divides the first thing, then by assumption of this line over here, there exists some q sub I such that p is equal to q sub I where that I is between 1 and k. In either case, if p divides that product, then there exists some q sub I such that p is equal to q sub I. Proof by induction.
It's way nicer than I thought it was going to be.
It's what?
I said that was way nicer than I thought.
Proof by induction is almost always nice. It's wonderful. We love proof by induction. It's very straightforward how you do it. You know exactly what the person's going to do. They're going to show some base case, they're going to assume k, show that implies k plus 1, they're done. Good? Okay, so now we're going to actually prove what we were trying to prove before, this thing. And I couldn't fit the whole proof over there, so I'm going to finish it over here when we get to finishing it. Had too much to cover today. Alright, proving this. Before we just stated the fundamental theorem of arithmetic, now we're proving the fundamental theorem of arithmetic. So, proof. If n is a positive integer, then n has unique prime factorization. That's what we're proving. Okay? Okay. First thing we're going to do is prove that it has a prime factorization. Then we're going to prove that that prime factorization is unique. So we're starting out with just it has a prime factorization. With me? So let x be the set of all positive integers that don't have a prime factorization. And I'm going to assume x is empty by assuming that it's not empty and get a contradiction. Smallest counterexample is what we're going to use. Yeah, we're using smallest counterexample. So let x be the set of all positive integers that don't have a prime factorization. We know x is empty. Let x be the set of all positive integers that don't have a prime factorization. And observe that 1 is not an x. How do I know 1 is not an x? We already talked about the fact that 1 has a unique prime factorization, namely the empty product. The empty product is always 1. So that's its one and only prime factorization, and that prime factorization only gives you 1. Okay. So we know 1 is not an x. since it's the empty factorization. And furthermore, we know that no prime number p is in x. Because what's the prime factorization of any prime number? Just itself.
Okay.
Right? So for sure, 1 and p are not in x. Obviously, because x is empty, but the ones that we know, 1 and p are not in there. Assume by way of contradiction that x is not the empty set. We know x is the empty set. Assume by way of contradiction that's not the empty set. And we're going to get a contradiction. So assume by way of contradiction that x is not the empty set, and let little x be its least element. We're doing the smallest counterexample. Now I know that x is greater than 1 because 1 wasn't in there, right? X is a positive integer that's not 1, so it has to be greater than 1. And I know that x is not prime because we showed that no prime numbers are in big X. So little x is the smallest thing in big X. We know for sure big X doesn't have 1 and it doesn't have any primes. Therefore, little x is greater than 1 and it's not prime. And we did a proof way back when we were talking about priming composites where every number greater than 1 that isn't prime is composite. So since x is a number greater than 1, sorry, we're up here. Since x is a number greater than 1 and x is not prime, then x is composite. Good?
Yep.
What does it mean for a number to be composite? A number is composite if it has two integers a, b, where a and b are between 1 and x, such that the product gives you x. That's what it means to be composite. What's an example of composite number? 6. How do I know that 6 is composite? Because there exist two integers, namely 2 and 3, that are between 1 and 6, such that their product gives me 6. Good? Okay, so a and b are two integers such that when I multiply together, I get x. Since a is less than x and b is less than x, they have a prime factorization. What is little x? Little x is the smallest number that doesn't have a prime factorization. A and b are numbers smaller than x, therefore they do have a prime factorization.
Yeah.
Am I losing you on that?
How come just because they're smaller than x, then they have a prime factorization?
Little x is the smallest element in big X. Big X is all the positive integers that don't have a prime factorization. So a and b are not in big X. So a and b do have a prime factorization.
Because they're smaller than x, so they're not going to be an x. Big
Perfect.
X.
That's exactly right.
Okay.
A and b are smaller than little x. Little x is the smallest thing in big X. Therefore, a and b are not in big X. Therefore, a and b have a prime factorization. We don't know anything about uniqueness yet, but they do have a prime factorization. So in other words, I can represent a as the product of a bunch of primes, and I can represent b as the product of a bunch of primes. And since x is equal to a times b, then x is equal to a product of a bunch of primes times the product of a bunch of primes, which is a prime factorization. So it has a prime factorization, contradiction. Follow me there so far?
Right.
Yeah.
So far, all we have shown is that every positive integer has a prime factorization. Now we need to show it's unique. So it's kind of like we're starting a new proof now. Okay? Okay, so now, since we already used x, I'm going to use y. Let y be the set of all positive integers, all k, where k has two unique prime factorizations. Maybe more, but it has at least two unique prime factorizations. Obviously, we know y is empty. We're going to assume by way of contradiction that it's not. Grab its least element. We're using smallest counterexample. Okay. So let y be the set of all the positive integers that have two unique prime factorizations. And by unique, we mean using actual different numbers, not just different orders. Order doesn't matter to us. Assume by way of contradiction that y is not empty, and let little y be its least element. What are we saying? We're saying then little y is equal to this prime factorization, and little y is equal to this prime factorization, where those are two distinct prime factorizations, right?
Yeah.
And notice that the p's and the q's are going to have no element in common. None of the prime numbers that show up here can show up here. How do I know that? Because I factor that prime number out of both of those. Y is equal to this, and y is equal to this, right? Assume that some prime number, say that 2 shows up over here and 2 shows up over here. Then divide y by 2, and you get 2 different product of prime numbers, which would be a smaller number than y. Y is the smallest number with 2 unique prime factorizations. So none of these can have common primes. Does that make sense?
Yeah.
Okay. So where the p's and q's have no common elements is what I was saying there. That's what that meant. Okay. So now we've got y being represented as 2. A little busy explaining, I just didn't think ahead for a second. So assume by way of contradiction, so that y can be expressed as 2 different products of primes. Then they have no element in common. Okay, now I'm just going to set them equal. Then, the first product of primes, Q1 times Q2, I don't think that's the first one. The first one's P, right? Then P1 times P2 times P times dot dot dot. What's my last one?
PT.
T is what I use. PT is equal to Q1 times Q2 times dot 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 times QS. Right? Because this is equal to y and this is equal to y. So these are both equal. So that gives me that P1, I can pick any one I want, but P1 divides this product. P1 times an integer equals this thing, therefore P1 divides this thing. P1 divides Q1 times Q2 times dot 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 times QS. Using our theorem right here, if P divides a product of primes, then P is one of those primes. So then that gives me P1 is equal to Q sub I for some I less than or equal to 1 less than or equal to I less than or equal to S.
Contradiction.
So P1 has to equal in those. Perfect. Which is our contradiction. Because those can't have any common elements.
Right.
If they did have any common elements, we could divide it out. We'd still have 2 equal numbers.
You get less than your least
And you
element.
get less than y, which is our least element. Follow that?
Therefore, y is empty.
Yeah. Therefore, every positive integer has a unique prime factorization. Every n in Z plus has a unique prime factorization. Okay, and we're done. Next proof. We're going to prove that there's infinitely many primes. This is a proof that Euclid did way back in his Elements. We're going to prove that there are infinitely many primes, and we're going to do this proof by contradiction. Prove there are infinite primes. 1. Assume by way of contradiction that there aren't. Assume by way of contradiction that there are finite primes. If there's finite primes, then that means that you can list all the primes 2, 3, 5, 7, all the way up to some final prime p, right? So let n equal 2 times 3 times 5 times dot 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 times p plus 1, where p is the last prime.
Y plus 1.
You'll see, because we just made a prime number. Notice n is not divisible by any prime number. When you divide n by 2, your remainder is 1. When you divide n by 3, your remainder is 1. When you divide n by 5, your remainder is 1. When you divide n by 7, your remainder is 1. N is not divisible by any prime numbers. But it has to have a unique prime factorization. So what is prime factorization? This. So n is prime.
So
n is
confused.
what?
N is prime. We just created a new prime number.
But you added 1, so
P
maybe
is our biggest prime. Look.
Yeah.
Okay. Assume by way of contradiction that there are finitely many primes. Right? And maybe I should have said somewhere in here 2. Let P be the largest prime. P is our largest prime. Okay. Now let n equal 2 times 3 times 5 times 7 times times P plus 1. Is n bigger than P?
Yes.
Yes. So if n's also prime, we're done. Right?
Yeah, because that makes contradiction because P is your
Yeah.
first prime.
So let me put that in there, and let's make this more clear. So 2. Let P be the largest prime. Let n equal 2 times 3 times 5 times, we're just saying the product of all the primes, up to P plus 1. Right? Question, is n prime? Or better question, what are the prime factors of n? Is 2 a factor of n?
Yeah.
Okay. What are the factors of 12?
2 and 6.
1, 2, 3, 4, 6, and 12. Those are all the factors of 12, right? Because they go into it evenly. 7 is not a factor of 12 because it doesn't go into it evenly. 12 divided by 7 gives you some remainder. Notice when I take n and I divide it by 2, I'm left with a remainder of 1. N is equal to 2 times something plus 1. When I take n and I divide it by 3, well, here I have n is 3 times some integer, whatever you get when you multiply everything else out, plus 1.
Okay.
So n is not divisible by 2, n is not divisible by 3, n is not divisible by 5, n is not divisible by 7, n is not divisible by p. But it has a unique prime factorization. None of these numbers go into it. Obviously, it goes into itself. So n is its own prime factorization. So it's prime.
Okay.
Does that make sense?
Yeah.
Wait a minute.
Okay.
Are you saying that there are an infinite number of primes that you can do for that? What you're doing at the very start?
I'm saying there's an infinite number of primes, period. We're saying there aren't finitely many prime numbers. In fact,
So
this
you're
algorithm gives
proving-
us a way of generating prime numbers.
So you're just proving that there's literally just an infinite number of primes.
That's it. That's all we're
Why,
proving.
why do we need to prove that?
How else would you know that there are?
Because there's infinite integers.
So, there could come a point where they start just being combinations of other integers. Think about what that says. That says that no matter how big of an integer you get, you're still guaranteed to find an integer bigger than it that can't be expressed as a combination of the integers that came before it.
Oh, I see.
You can't multiply the integers before and get it. It's its own individual integer. Its only factor is itself, and 1. Like, that's not something that's just obvious from thinking about the integers.
That's true.
Something that needs to be proved. So now we just proved it. There are infinitely many prime numbers. And this tells us a way that you could generate infinitely many prime numbers now. Because start out with any prime number that you know is a prime number, 2. So now I know 2 plus 1 is also prime, which is 3. Now I know 2 and 3 are prime, so 2 times 3 plus 1 is also prime, which is 7.
Oh.
Now I know 2, 3, and 7 are all prime, so 2 times 3 times 7 plus 1 is also prime. And what's 2 times 3 times 7? 43. Now, this doesn't give us all the prime numbers, but the point is I could go on in this fashion forever generating new prime numbers. So it gives us a way to generate them.
That's crazy.
Okay. Last proof we're going to do is that the square root of 2 is irrational. We've already done a proof of this. Now we're going to do a proof using the fundamental theorem of arithmetic.
Square root of 2 is irrational.
Is it
Why
irrational?
are we
You
proving
mean
this?
undefined as irrational?
The square root of 2 is not a rational number. It is irrational.
Ah.
Why are we proving this in this course? Like, that seems so random.
Number theory?
That square root of 2 is irrational.
Yeah. That it can't be expressed as a quotient. You cannot find two integers, a and b, such that a over b gives you the square root of 2. And that, once again, is not trivial. Because I can keep finding quotients of integers that get closer and closer to the square root of 2. And I can get as close to the square root of 2 as I want, but I can never quite get there,
That
which is
seems
rational.
a little random to be connected to this.
Oh, it's just, it is kind of random in the sense that we're not,
We're not even talking about something like that.
well, it's just going to be a consequence that's really easy to prove with this fundamental theorem of arithmetic.
Okay.
So it's just showing you a use case of the fundamental theorem of arithmetic. I mean, I don't know why it's any less valid than there's infinitely many primes.
That's why she asked that too.
Alright, so that should be enough space to do
Well, at
it.
least before we were talking about primes. That would make a little bit more sense.
Proof. While we're talking about integers, let me state it differently. I cannot find a quotient of integers, a and b, such that when you square them, you get 2. Okay. Prove that there are no integers a, b that make this true. That's what we're proving.
Okay.
Okay, now we're just talking about integers and squaring them. Okay, proof square root of 2 is not rational. That's what we're proving. Assume by way of contradiction that it is. That the square root of 2 is in Q. What does that mean? That means that there exists AB such that A over B is equal to the square root of 2. That's what it means for the square root of 2 to be rational. It can be expressed as a quotient of integers. Right? Square both sides, and that gives me that A squared over B squared is equal to 2. Or in other words, that gives me that A squared is equal to 2 times B squared. Right? Now, I don't know if we need to really write anymore to just explain how this is a contradiction. A has a unique prime factorization, right?
Yeah.
So, in A squared, 2 shows up an even number of times. If 2 shows up an odd number of times in A, square and odd, what do you get? Oh, wait.
I'm confused.
It is true, but I'm saying that weird. So let's say that A is equal to 2 to some integer A times some other primes as a prime factorization. And 2 shows up as prime factorization, not A times, sorry, we already used A. A number we have to use C. So either shows up 0 times, or 1 time, or 2 times, or 3 times, or 4 times in A's prime factorization. So in A squared, it's going to show up how many times?
Twice.
2C times. That's the way I meant to say that. So 2 shows up in A squared's prime factorization an even number of times. Possibly 0, 0 is still even. Make sense?
Yeah.
2 shows up in B squared's prime factorization an even number of times.
And then it made it odd.
But then we have an odd. These two numbers are equal. They have to have the same prime factorization. But this has an even number of 2s, this has an odd number of 2s. Contradiction.
Okay.
So there's another way to prove that. Okay, that's it. Maybe we'll use the rest of class actually to go over your test because